Hi to everyone. My name is Carlos Mauricio Correa. I work at the Instituto de Astronomía Teórica y Experimental in Córdoba. I have a postdoc position here. I have recently defended my PhD, so today I'm going to explain one of the main results of my research. This work has been done in collaboration with Dante Paz, my PhD supervisor, and also with Ariel Sánchez, Nelson Padilla, Andrés Ruiz, and Raúl Angulo. Here I leave you the link to the paper if you are interested in more details. So let's start with the problematic and goals of our work. Well, the dark energy problem is one of the major challenges of modern cosmology. And in this sense, cosmic voids are promising cosmological proofs. However, there is an obstacle that has prevented using voids as reliable tools. Our standard picture of distortions around voids is incomplete. We have focused only on the galaxy spatial distribution. But the truth is that distortions also have an impact on intrinsic void properties, such as their number, size distribution, and spatial distribution, generating in this way additional distortion patterns in observations, which can lead to biased cosmological constraints if they are not taken into account properly. So in this work, we tackled this problematic, trying to find a physical connection between the identification of voids in real space and the identification of voids in Redshift space using a spherical void find. This a priori is not trivial to do, because unlike the case of galaxies, which can be considered particles that are conserved under the Redshift space mapping, only their position changes, the case of voids is very different, mainly because voids are extensive regions. So in this process, some voids can be destroyed, whereas other artificial voids can be created. So it is not trivial to assert if both void populations are really the same. In fact, we know that they have very different statistical properties. One of the main results of our work was to realize that each Redshift space void above the shot noise level has a unique real space counterpart spanning the same region of space. In other words, we have found a one-to-one relationship between voids in real and Redshift space. And this is very important because this means that under the Redshift space mapping, voids are conserved. And this has a very profound implication because then the differences in the statistical properties between both void populations can only be attributed to some physical effect that transform real space voids into the corresponding Redshift space counterparts. Such effects can only be a consequence of the distortions. So a physical description can be found from cosmological and dynamical considerations. From this schematic illustration, it is easy to see the two main effects. First, we have a systematic expansion, and then a systematic off-centering in the line of sight. Let's start with the systematic expansion. So this effect is a byproduct of the Redshift space distortions induced by the dynamics of the galaxies surrounding the void. For this reason, we also refer to this effect with the acronym TRST, T for tracer dynamics. Starting from the velocity profile that characterizes the velocity field around voids, it is possible to quantify analytically this effect. We found a linear relation between void radius in Redshift space and void radius in real space, where the constant of proportionality depends on a fundamental cosmological parameter, beta, the growth rate of cosmic structures. But this is not the whole story. The volume of voids is also affected by the Alcock-Paczynski effect when selecting fiducial cosmology to establish a physical distance scale. However, reasoning similarly to the expansion effect, it is also possible to quantify analytically this effect too. We found, again, a linear relation between the fiducial and real space radius, where in this case, the constant of proportionality depends on the background cosmological parameters, such as omega matter. But unlike the expansion effect case, the Alcock-Paczynski change of volume effect can manifest as an overall expansion or contraction depending on the fiducial parameters chosen. What is important to keep in mind here is that in practice, both effects appear coupled in observations. So the final relation between void radii in real and Redshift space must take into account these two factors. And finally, the last effect, the off-centering effect, can be simply understood if we consider that voids move through space with the net velocity as whole entities. So this effect can be considered a byproduct of a new kind of Redshift space distortions induced by the global dynamics of voids. For this reason, we also refer to this effect with the acronym BRSD, B for void dynamics. And to quantify analytically this effect, all we need to do is to write down an equivalent equation for the RSD shifting of tracers, but applied to the case of the void centers. Here we see that in this equation we have the net velocity and the cosmological dependence. Okay, now I am in a position to explain the distortion patterns that these effects imprint on the void statistics. Let's start with the void size function. The void size function characterizes the abundance of voids in the universe. Here in this plot, you can see the void abundances measured from the Millennium Extra Large simulation. Here, the blue curve is the true real space abundance, and the other curves are affected by distortions in different ways, so they mimic possible observational measurements. Note how different they are. So it is mandatory to correct these abundances in order to recover the true real space one, the blue one, with the three Redshift space effects that I explained before. This correction is mandatory. Fortunately, in the case of the void size function, the off-centering effect does not play any role, because all we are doing here is treat void. So we get here a very simple formula to correct void abundances, that is the relation between void radii in real and Redshift space. Remember that this correction depends strongly on the cosmological parameters, so it must be incorporated in current models based on the excursion set theory for the void abundances in order to obtain unbiased cosmological constraints. This correction works very well at all relevant scales. Now, let's move on to the other void statistic that we are going to treat in this work, the void galaxy correlation function. Here, I show you some preliminary results from observational data, specifically from the Baryon Oscillation Spectroscopic Survey, using the projection method, a method that we defined in a previous work. Specifically here at the left, you have the plane of the sky projection of the correlation function, and at the right, the line of sight projection of the correlation function, which is extremely sensitive to all types of distortions. So as we did in the case of the void size function, in order to model properly these correlations, we need to take into account the three Redshift space effects that affect voids that I explained before. Note here that if we only model the Alcock-Paczynski and expansion effects, as has been traditionally done in the literature, it is not sufficient. Although the plane of the sky projection is well described by the models, the line of sight projection is not. Here you can see a very important deviation, very significant deviation. And this highlights the importance of detecting and modeling all types of distortion. In particular, in this case, we clearly see the importance of modeling the off-centering effect. This is the first time that this new kind of distortion pattern is detected in observations. And we have a very neat signal to detect and study this effect. By the time we have made some progress in modeling the off-centering effect, and we realized that there is even more. In the case of the correlation function, there is a fourth source of distortion patterns that is related to the intrinsic ellipticity of voids. So to finish my conclusions, cosmic voids are promising cosmological proofs to test the dark energy problem, but our standard picture of distortions around voids is incomplete. Distortions do not only affect tracers, they also affect intrinsic properties of voids, specifically their size distribution and their spatial distribution, generating in this way additional distortion patterns in observations that can lead to biased cosmological constraints if they are not taken into account properly. In this work, we tackled this problematic, finding a physical connection between the identification of voids in real space and in Redshift space based from dynamical and cosmological considerations. Well, if you are still here, thank you very much for attending my talk. And if you didn't understand anything about the Redshift space effects in voids, don't worry, I think this figure will help you. Thank you very much.